Today we're going to explore a powerful computer science idea called recursion. And recursion basically means that we're defining something in terms of, usually we like to avoid circular definitions and define something in terms of something else, but here we're going to define something in terms of itself. And we're going to see that's actually a surprisingly useful idea. And to begin, let's explore what happens in a little world with a robot. In fact, let me bring my robot on the screen just in case you haven't seen any of my videos using the robot, so that you have an idea of what I'm talking about. Here is a world in which there's a robot slightly cut off maybe from what you can see there. Let's say, oh, it's not going to let me grab this window and show you. That's okay. Here we have a robot. And that robot is apparently in some corridor with some number of squares, and I can instruct it to do things like move, and my robot takes a step. I can instruct my robot to turn left, and that's pretty much all I can do, but I can define new instructions like turn around, turn around, and back up. Let's look at back up, and we should see it take one step back, albeit by turning left twice, moving once, and turning left twice again. Alright, so that's our little robot world. And what I want to explore is what happens when we define a method that, I'll just call it mystery since I don't know what it's going to do yet. Could do anything. What happens if I define a method that calls itself, that when asked to perform this task mystery, Java's going to perform mystery? And you may feel like that probably doesn't accomplish anything. Let's see if you're right. So I'm going to hit the compile button. It's off screen right now. And I will, you know what, this one doesn't even seem to involve the robot, so I will just call my method. And since my method is in a file called recursion, I'm calling it by writing recursion dot, and I can do that because it is a static method, recursion dot mystery. And this is what happens when you ask mystery to mystery. So let's scroll through that a bit. So first we called the mystery method in the recursion file, and on line 18 it called the mystery method in the recursion file, which on line 18, and you can see it kept calling itself and calling itself and calling itself, and eventually Java got upset, and we see something called stack overflow. That's because every time we call mystery, Java makes a note that when it's done well, actually, this will be more obvious when we do a further example. So let's do a further example. What if I have mystery, call itself, and then move the robot one step? Call itself, and then move the robot one step. So I'm compiling now. Good, it's compiled. I'm going to load my little world. I think it was called hall.txt. It's off screen. There it is. There's my little world with the robot slightly cut off from your view, but I think you can tell what's going on. And we will try now to call this mystery method. And the mystery method calls itself and then moves. There we go. Oh, that looks like exactly the same behavior. So here's what's going on. In order to mystery, Java realizes it first has to mystery, but when it's done mysterying, it's going to move. So before it calls mystery, before it makes what's called a recursive call, before it calls itself, it makes a note that when it's done, it's going to move. And then inside of that call to mystery, it realizes it's going to call itself again, but it makes a note that when it's done calling itself again, it's going to move. And so every time it calls itself, it makes a note that when it's done, move. So all those notes that say, when I'm done with mystery, move, they all get written somewhere in memory. They all get written to a place called the stack, and they accumulate, and they accumulate, and they accumulate, and eventually Java runs out of memory to write down all of those places where it's remembering to go back and move when it's done mysterying. And that's why you see this stack overflow error right here. Alright, let's try some other things. What if we move and then mystery? Move and then mystery. So I will hit F5, that will compile. Good, it's happy. And we will, I guess we better load our little hallway. Make it appear on your screen, although it's slightly cut off. It's not really going to let me move that easily, so we'll just show you it cut off. And we will ask it to perform mystery, which is going to move and then mystery. Any guesses what it will do? Is it going to move? Move once? Never move? Hey, it seems to be moving a whole lot of times. So let's see, here you can see on line 19 of mystery, it called mystery, which called mystery, which called mystery. But in between each of those calls, it first moved and then called mystery. Move and then called mystery. That's why we see it moving. And eventually, it calls move and things go wrong because it tries to move to an invalid location and it hits the edge of the screen and the program stops. But this is an indication that recursion might actually be a really useful idea because we saw it do something useful like repeatedly move. And the amazing thing about this code is there's no loop in this code. There's no loop. We said move and mystery. We didn't use a while loop or a for loop, and yet we got repeated behavior. We got it repeatedly moving. So that's a very powerful idea. And let's make a note of that. The big idea of recursion is that we can use it to result in iteration looping behavior without actually writing a loop, like a for or a while loop, if you know what those are, explicitly in our code. Now, you may not be super impressed because maybe you prefer to use for loops and while loops and you don't know why you would want to use recursion to avoid those things, and maybe you're not convinced that you could use recursion in place of for loops and while loops to do anything but crash into walls. But it's going to turn out that any problem that can be solved with a loop, for or while loop, can be solved without it, recursively, by defining a method in terms of itself. And, equally important, any problem that can be solved recursively can also be solved with a loop, a for or a while loop. So these are reasonable alternatives. We can always choose one or the other. Either way will work, but sometimes one way will be harder than the other. And we'll explore many such ways, but first, let's convince ourselves this might actually be useful. So the problem is, when my robot gets to the end, it crashes into the wall, and you can't see it, but there is actually a wall at the top of your screen. When the robot gets to the end, it crashes, my program stops, and it's very sad. So maybe I can tell it, only do this business if the front is clear. If there's nothing in front of the robot, there's no wall, you're not about to get to the edge of the screen, then move and mystery. Actually, just for fun, let's write it this way first. If there's nothing in front of the robot, move, and then when you're done, mystery. If I compile, I just compiled, if I compile that, and I load up my hallway, there it is, and we run mystery now, there it is. It's still looping, and it doesn't crash into the wall at the end, but if we scroll, we can see it eventually does make a bunch of notes. So first, while the front is clear, it moves, which is nice. Calls mystery again. If the front is clear, it moves. Calls mystery again. Eventually, the front will be clear. It will get to the end, and now it will stop moving, and it will simply be as if we just wrote mystery, calls mystery, which calls mystery, since the front will never be clear again. And we'll see that same Stack Overflow we've seen many times. The key idea is that we'll take the call to mystery and put it inside the if. So now it says, if the front is clear, move and call mystery again. And the reason that's a powerful idea is because there's a case where we call mystery, where mystery is defined in terms of itself. But there's a second case, and it's sort of hidden here, but there's the else case that says, don't do anything, do nothing. In the else case, it's not defined in terms of itself, and our program will not call mystery again, and we'll stop, and we'll see what happens. So I've compiled again, I'm loading my little hallway again, and I'm instructing it to perform this mystery method, and we'll see what it does. So notice this time it also got to the end and stopped, but here it didn't crash into a wall by going off the screen. It didn't have a Stack Overflow because it kept calling mystery over and over again. It actually eventually got to doing nothing, and the program stopped. Well, that's amazing. Why does it work? What we've basically written is, it's not really mystery, it's move to the wall. And what does move to the wall do? Well, if the front is clear, it moves, and then it moves to the wall. And I'm going to get rid of this piece down here. since it wasn't really doing anything else. Do nothing is unnecessary to say that. So this says, in order to move to the wall, if the front is clear, move, and then having moved, the remaining work is to move to the wall. So it's not completely defined in terms of itself, because we only have the method call itself in the condition that it's not already at the wall. If it's already at the wall, this code will stop because the front won't be clear anymore. And before we actually say, in order to move to the wall, we first take a step. So here's a case of, we might say that the longest journey begins with but a single step. Moving to the wall, this long journey, begins by making an actual movement, moving one square, and then having moved one square, we can now move to the wall, and move to the wall will move one square, and move to the wall, which means move one square, and eventually we'll call move one square, the front won't be clear, and the program stops. In our next video, we'll take a look at exactly how this works. We'll convince ourselves that this really works, and get to know recursion better. I will see you in that video.